So as most of you know at this point, that it's the High Frequency Active Auroral Research Program. And I am the Deputy Director of the Geophysical Institute, and HAARP is one of our operational facilities. So I'm just going to cut to the chase right here and say, let's talk about conspiracies. There's all sorts of conspiracy theories about HAARP. I don't know why. I don't get it. But they're out there. It's even to the point where people have written books about it. So for me as a space physicist, we've often gotten conspiracy theories about some of the things that we do, the experiments or the science that we do. HAARP is particularly wrought with it. I don't totally understand why. It does detract a little bit from the science. So is HAARP a government conspiracy? No, it's not. We don't practice mind control. As it was pointed out at the iHAARP radio, they did a interview of me this morning, and he pointed out that if I actually had mind control, then the university would not have a budget problem right now. I said, yeah, that's a really good point. Thank you for that. But there is, neuroscience is a complex field, and there are medical professionals who do that. We are not medical professionals, and we do not do mind control or neuroscience of any kind. Weather control, we'd have a better summer if I had weather control. Earthquakes, flooding, hurricanes, no, we don't do any of that. So radio waves are in a frequency that transmit through the water part of the atmosphere, and we'll talk about that a little bit more. Alien landing pad, I'm not even sure where that one came up. I don't know what to say to that except no, not an alien landing pad. And we don't do chemtrails. What you see up in the sky are contrails. They're the water vapor from the engines, from the airplanes, just like what you have for cars, ice fog. We're all familiar with that. So no. Ionospheric research, yes. That is what we do. So let's talk a little bit about that. What we see is the troposphere and the stratosphere, and you can see Alaska Airlines there. The Earth is just below it, or an airplane, but for me, it's Alaska Airlines. And that's where we are with, in the airplanes, that's where the weather is. You see the clouds, you see the weather balloon, and there's even a sounding rocket. I didn't know that Tom Hallinan was going to be here, but it's good that we have this for him. So let me see if I can undo what I just did. There you go. So this is all the atmosphere, but the ionosphere is what we're interested in. So we have the D layer, the E layer, and way up above on that screen is the F layer. And that's the ionosphere. That's what we're looking at with HAARP. So the aurora happens way up here, and weather happens way down there. So we cannot control the weather because we're not even in the area of the atmosphere in which that happens. So what does HAARP do? I've talked a lot about what it doesn't do. What does it do? Well, HAARP makes changes to the ionosphere, and scientists use that to observe and to test. So we're testing different ideas, different models. We're testing technology, and we're observing, learning about the fundamentals of plasma physics. So it's a high-frequency ionospheric heater. We're going to talk a little bit more about that. I'm going to kind of go a little bit into history of HAARP and a little bit into the science, and hopefully you'll have an overall better picture of what it is that we do there. The ionospheric heater changes the temperature, that changes the conductivity, it changes how the currents move, and that again changes how the radio waves interact. And that's really the basis. So let's start first with the ionosphere. There's a couple of people in this room who will agree with me on that first bullet. It's one of the most interesting layers of the atmosphere. It's partially ionized, and it's above 600 kilometers. It's influenced by radiation from space. It's affected by electric and magnetic fields. And in turn, it influences us by interacting with our technology. It plays a role in modern day communication. Is it safe? Yes, it's safe. Health and safety were our primary focus in building and deploying the transmitter and the antenna array. And we're going to talk a little bit more about it. There'll be some photos. But the concept is it's a fixed system, and the field strengths decrease in a known manner with distance from the antennas. So let's go back to the ionosphere. Why do we want to change the ionosphere? First, before we get too far into that, we are going to talk a lot about how we change the ionosphere, but the changes are small and they're temporary. They mimic natural phenomena, but they're much smaller in extent and in power than what happens naturally with the aurora. The motivation for doing this comes from both scientific and practical considerations. I put that in there because as a scientist, I understand that I'm not often considered practical. So as a basic researcher, we're interested in the science of the plasma. We're interested in what's happening, what are the physical mechanisms, what are the causes and effects. And on the practical side, the irregularities in the ionosphere, they change the way that the radio waves and some of the satellite communications happen. So when that happens naturally, there is break in communication, and we're studying that. How does that happen? Why does that happen? And is there a way to predict or prevent? I often get asked why don't you do these studies in the lab? Why do you need to go out and do this to the real ionosphere? And my comparison is, there are some things that you can do in a lab, like with a wave tank. But if you think about being in the bathtub and about how the water, the waves will hit up against the walls and create additional waves. And if your phenomena that you're studying is bigger than the bathtub, then the waves and the interactions from the walls itself will stop you from being able to do that work. If they're smaller than that, that's fine. You can do it in a wave tank or you can do it in the lab. But if they're bigger, you need to go out, say, to the ocean and study the waves in the actual ocean. And it's the same way with the ionosphere. The things that we're studying, the phenomenon, and the wavelengths that we're talking about are much larger than what you can do in a lab. So we need to have no walls. We need to have it in a natural environment. So why do we do this? Well, to put HAARP and the Geophysical Institute in context, I want to take a couple steps back in history and kind of lead you along the path of how we got there and why we got there. Back in 1935, they discovered something that's called the Luxembourg effect. And it was really before the discovery of the ionosphere. So there were people in England who were listening to a radio station that was being broadcast from Luxembourg. And there was another radio station in Paris that was broadcasting at the same time, but it was on a completely different frequency. So if the air and the atmosphere is neutral, without charge, there should have been no interference between what was being broadcast from Paris and what was being broadcast from Luxembourg. But the people in England heard both channels at the same time. And it's now called ionospheric cross-modulation, but at the time it was a question, it was a puzzle. And scientists love a good puzzle, right? So this is really one of the things that was happening that was unexplained by the theory of the atmosphere at the time. So just to put the Geophysical Institute in historical perspective, now here's where I have to admit that when I was preparing for this talk, I started reading into this history of the Geophysical Institute, and I dug really deep because I found this very interesting. You will not often hear me say that I find reading history very interesting, but this was fascinating to me because the names were all so familiar to me. The people who were involved in this history and in the building of the Geophysical Institute and this university are all very famous scientists. It made me feel very, very good about where I am and who I work with. So that's just a little personal note. But in the 1930s, there was a professor who was at the Alaska Agricultural College in School of Mines who started auroral studies. That's a little bit crazy pants, right? But it's kind of how it started. We are in the Arctic region. We are within the auroral oval, so it's interesting. And that's how it started back in the 1930s. Remember, the Luxembourg effect was in 1935, so it's all about the same time. There was an international polar year and the scientific years are always 18 months. I can't explain that. But the international polar year was 18 months in which we focused on the polar region. And in the period between 41 and 46, the College Observatory was constructed, and it was to help the war effort. The Geophysical Institute was created by an act of Congress in 1946, and it was really focused on Arctic studies, which, again, it was an agricultural college and a school of mines, but it had this auroral aspect to it. So what started happening is it started to really focus on radio science and auroral physics. And then we had a long succession of famous and influential physicists who were right here in Fairbanks, Alaska. It's very exciting. And this is one of my favorite quotes. This is from Keith Mather, who was director of the Geophysical Institute. And he was writing about Sidney Chapman, who was a previous director. And just the idea that we had CTLV and Sidney Chapman here working together. It was called the Chapman-LV era in the 1950s because they brought the Geophysical Institute and the University of Alaska Fairbanks to the forefront of science on a global level. It's pretty amazing. And Keith is saying how just the mere presence of having Sidney Chapman here brought up the scholarly level, created a culture, created that intellectual environment. I find this very exciting. And then, so Keith is saying this about Sidney, but here's the truth. Keith, when he was director, he expanded the Geophysical Institute, which was basically focused on radio science and auroral physics. He expanded it and brought in all these other disciplines. So the disciplines that we have now, we have 7 discipline groups at the Geophysical Institute. It includes atmospheric science, remote sensing, which is the group that I'm in, seismology, snow, ice, and permafrost, space physics and aeronomy, which is really how things started, tectonics and sedimentation, and volcanology. And if you notice, all of these disciplines are geophysical in nature, and they're related to the Arctic in some way. And if you remember, I don't have to tell you guys this, but when I'm in the lower 48, I say this all the time. Alaska is the reason why the US is an Arctic nation. And so we're important in the science world, we're important in the political world. So while we're growing all these disciplines, we're also growing the operational programs. And although I'm not going to talk a lot about any of these except for the one in the middle, I just have to point out to you that one up there in the top, Alaska Satellite Facility, super interesting. That's the one I'm the director of. But we are going to focus on HAARP, which is right there in the center. So I've talked a lot about the Geophysical Institute. You're inside the Murie building, which is part of the Institute of Arctic Biology. And there are a couple of other institutes that are either inside or outside of colleges, but the truth is that research is an integrated core function of this university. We are the research university of the University of Alaska, and it's really our primary focus. Doing basic research is in our DNA. Today, the GI, we have about 375 employees, 65 faculty, but 100 PhDs, because not all the PhDs are faculty, myself included. Been in these 7 groups and 9 operational programs. We have about 10 other facilities that are smaller facilities or programs. But let's get back to HAARP, or get on to HAARP. So HAARP was a joint Air Force and Navy program, and it ran from 1990 to 2014. Its goal was to look at the physical and electrical properties of the ionosphere that can affect communication and navigational systems. And its location was Gakona, Alaska. Why Gakona, Alaska? And people ask me that actually when I was showing this to my staff earlier today, before I could even turn this to the slide, they said, why Gakona? I'm like, okay, thank you. Can you be there tonight at about 7:20 and prompt me? So actually, it's a location. It's within the auroral zone, which is important for the studies. Near a major highway, you Alaskans know how important roads are, right? It's really important to be able to drive to something because there's a lot of places we cannot drive to. It's away from cities, which is kind of something that doesn't always happen in Alaska. If you can drive to it, there's usually a city there. So it's a nice location. It's flat terrain, and it has minimal environmental impacts there. So that's why Gakona. It's actually quite beautiful. I went on Monday, right? Jessica Matthews is here. She's the director of HAARP. Thank you. And she drove me both ways, had to listen to me talk the entire time, both ways. So I appreciate it. It was a beautiful trip. So HAARP, I remember I told you that it started in 1990, and the construction really began in 1993. That's usually how things go. And the first part of the functional facility was completed the winter of '94. So between '99 and 2004, there were over 20 major research campaigns that were conducted, and they ranged from 15 to 130 days. It depends. The actual facilities themselves are worth about $290 million. It's the land, it's over 5,400 acres. And the ops center is very large and accommodating with a 12 megawatt power plant. And we will talk a little bit more about the power as we go. But remember, this was Air Force and Navy working together. But then there was a transfer from the Air Force to UAF. For over 25 years, the Air Force and the UAF collaborated on research, ionospheric research out at HAARP. So when the Air Force decided that the funding and the development needs had decreased, there were efforts made by UAF and the research community to preserve this one-of-a-kind research tool. So the responsibility for HAARP was transferred on August 11, 2015, and it's under an educational partnership agreement. And we put in place something that's called a CRADA, which is it's an agreement that provides access to government-funded resources that can be leveraged, and they can have very powerful results. So to get an idea of what the facility looks like, the part of HAARP that we often think about as HAARP is this big array of antennas is what's called the Ionospheric Research Instrument. But it's only part of HAARP. There's an operations center, and there are diagnostics equipment that is used to observe the experiments that are being created by the Ionospheric Research Instrument. And there's an aircraft alert radar. So it's huge. And as far as the power is concerned, I talked a little bit about the power. There are 5 generators that power the IRI. And this is me. So I mostly wanted to show a picture of me, not because you need to, because I'm right here, but mostly for scale. You can see how large this engine is. This is 1 of 5. And this particular one comes from a locomotive. And the others, I think, are ships. Is that correct? They came from. But they're huge. And this is how the array is powered. So it's diesel engines, 5 of them out there. So what's with all those towers and antennas? What's going on there? It's a phased array, and it has 180 high-frequency cross-dipole antennas. What does that mean? So there's 33 acres, and it's capable of radiating 3.6 megawatts. And each of those trailers that are the the white boxes there, that contains all the electronic equipment for 6 of the antennas. So every one controls 6 antennas. And phase array is a way to put the radio profile on each antenna to be such that instead of 180 beams up into the ionosphere, you have 1. So you can focus them. So we phase them together so that the waves add and subtract in such a way to make 1 beam. This is this is my new puppy, and her name is Nike, but it gives you an idea of the size. So she's 4.5 months, 25 pounds. She was running around the array. She does love long walks, squeaky toys, and she loves HAARP. So it kind of gives you an idea of the size of these antennae. You walk underneath the antenna, they're quite large. So the UAF has ownership now of this incredible diagnostic tool. So what have we done since 2015? Well, we first had to restore the site safely from its mothball status to its operational readiness. All the tubes were removed from all those white trailers. Everything was removed by the Air Force because they were shutting it down. There were literally bulldozers there ready to take it down. The scientific community, led by Dr. McCoy, protested and said, no, you cannot take this amazing research facility down. So under the leadership of Jessica Matthews, they have rebuilt this and is operational, and we have so far conducted 3 successful research campaigns, 2 in 2017, 1 in 2018, and then there's another campaign that'll happen later this year. So who does this? University physicists, engineers, students, government scientists, and scientists from commercial organizations. And we have university partnerships all across the United States. It's a very, very unique tool. It's the only one of its kind in the United States, actually in the world. And it's incredibly powerful, so many people come here to use it. So let's get back to the science. Sun-Earth magnetic interactions. I'm assuming that everybody's seen this. I actually lived and breathed this for about 8 years of my life while I was in graduate school. So to me, this is a very, very familiar image. Not everybody has done that. I found out today because my staff thought it was a picture of a wine glass. I was like, I see it now, though. I mean, I see the wine glass, but I didn't see it before then. But what you have over here is the Earth and its magnetic field, which is a dipole. We've seen those with the magnetic shavings that you played with as a kid. And we have a dipole, but the sun emits a great deal of electromagnetic energy, and it distorts the Earth's magnetic field, and it looks something like that. And it's not a steady force. The sun it's very turbulent, and it keeps pushing, but it's sporadic. It has big bursts, solar flares, prominences, etc. So if you have extreme ultraviolet light from the sun and it hits the Earth's upper atmosphere, it ionizes. It ionizes a portion of the gas. And it goes from a neutral gas to a charged gas. And this is really important because its behavior changes. A neutral gas doesn't care about electric fields, doesn't care about magnetic fields, doesn't care about other charged particles, but an ionized gas reacts to all of those. So in an ionization process, you have the, let's see, it's on your right? No, left. Sorry. On your left, the atomic nuclei is neutral. The red in the middle has the plus charges, the blue on the outside has the negative charges, and they are the same number of pluses as minuses, so it's neutral. Electric field does nothing to it. On the right, you've got radiation that has hit that nuclei and popped an electron free. Now you have a positive ion and a negative electron, and these particles do care about magnetic fields and electric currents and radiation. So that's our ionosphere. the ionospheric layers that we talked about. And there are variations in the ionosphere that occur naturally. They occur seasonally, they change. They occur, changes day and night are different. If you notice, there's three main regions, remember from that first slide that said D, E, and F were the ionospheric regions, and they are different in day and night. They have sporadic changes that happen naturally that cause things like bubbles or patches, where a bubble is something that has less density and a patch has more density. And these are all throughout the ionosphere, all caused by the interaction between the sun and the Earth's magnetic field and the Earth's atmosphere. So radio waves are reflected by this charged layer. That's how you can take signals farther than just line of sight. You can use the ionosphere in radio to make that signal goes farther. And microwaves, I put this on here because it's important to know when we're talking to satellites. Most satellites talk to the Earth using microwaves, and they actually go through that. So the size of the wave and the density of the ionosphere matter in terms of what gets transmitted through, what gets reflected back. So lower frequencies and longer wavelengths, radio waves rather than microwaves, and they're reflected off of the electrically charged upper atmosphere of the ionosphere. So that also, though, depends on what frequency and what wavelength they have. So it depends on what you're transmitting. So if you see the yellow, that's a low frequency, and the wave is reflected rather low. And as the frequency gets higher, it goes higher up into the ionosphere, and it can even actually escape, depending on what's happening. So there's sky waves, there's space waves, and it depends very much on the atmosphere and the frequency. So why do we care? Well, there's a disruption of signals that happens. GPS signals, for example, are sensitive to ionospheric fluctuations. Signals are lost or disrupted because of variations of the plasma density. That happens with solar flares, prominences, and changes in the solar wind. Studying these variations and their causes helps us to understand this. And it helps us to eventually predict what's going to happen before it happens. So just as a visual, for ionospheric irregularities, it's really sad that everything gets cut off on the top. But in a GPS satellite system, there are many satellites. And there may be disruptions or bubbles or patches in the ionosphere that the GPS satellites are trying to talk through, and some of them are affected and some of them aren't because they're physically different sizes, different extent, different duration. So this kind of gives you a picture of what happens when you have structures inside the ionosphere that block some of the signals from the GPS. And now this is an example. This was actually detected at Poker Flat. It was an example of an ionospheric heater-induced air glow. Air glow is kind of like the aurora. So when you think about the times that you've gone out at night and looked at the aurora and it fills the sky. It's absolutely intense and it's beautiful and it moves and it's very large. That is a lot more energy than we can do at HAARP. But we can, in fact, create an air glow. Compared to a night sky full of aurora, this is a little disappointing. But to the scientists who got it to work the first time, this is pretty exciting. So this is what it looks like when HAARP is lighting up the ionosphere. And so a lot of the work that's done and put into making these planned irregularities in the ionosphere, it's very temporary. It happens very quickly. Some of the effects, the longest an effect has ever lasted is about 10 minutes, but usually it can be just a couple seconds. So why do we do it? We do it because if you're studying these kind of irregularities and you are waiting for Mother Nature to hand you one in the sky that you happen to be looking at, that's a very long career. It takes a very long time. And you have to be very patient and wait for it to happen. And you may not be able to put enough of those observations together.
Is there any color in that?
So yes and no. This is actually black and white, but honestly, it's the same color. If no, I know. If you were watching it, it would look white. Yeah, just white. Yeah.
No other color?
No.
Okay.
Yeah. So like I say, aurora, way more exciting. Unless you're the scientist who did this, in which case this is amazing. Yeah.
Were you observing any effect of resonance on your HAARP transmitter?
Oh, hold on. We're going to make you talk into the mic.
No, I'm going to have you repeat the question.
Oh.
And I'm going to have you use this instead of... Your finger looked like it was cramping.
Oh, yeah. I probably can't move my hand now. Okay, I'm sorry.
Yeah. To get that glow, were you observing any resonance caused by the HAARP antennas transmitting into the atmosphere?
That's a really good question. I'm not the scientist who is on here, but I can tell you that what you're seeing here is actually the ionosphere being heated in that location, and so that's what's being done.
Right.
Are you talking about?
Like, in regular radio.
Yeah.
Resonance.
Right.
You can pump it with your HAARP antenna and make it absorb more energy.
Yeah.
Is your HAARP tunable?
Yes. Yes, it absolutely is tunable.
You can sweep through a bunch of frequencies.
You can sweep through a bunch of frequencies, and it depends also. You can actually move the beam as well. You can you can do those two things, right? Move the beam and also sweep through the frequencies, which have a slightly different effect. So you can look at basically different heights by doing that. But I know that for at least this experiment, that everything is very transient and very quick to, you have to be looking at it, you have to be observing it while it's happening. It doesn't stick there.
Thanks.
I'm not sure I'm answering your question.
Yes.
But I think for me, when I'm looking at these airglow results, that the real story is, if you think about taking one of those immersion heaters that you would have to make tea in your dorm room. Did you guys have those? I had those. And if you take that heater and you put it in the Yukon River, you're going to heat a small part of the river for a short period of time. And that's essentially what we're doing in the ionosphere. So from my perspective, Alaska is a fantastic laboratory. And in this case with HAARP, it's an ionospheric laboratory. And because we saved the HAARP facility, we have a fantastic equipment to work in that lab. The GI owns the HAARP facility, and we can conduct campaigns at any time, and that includes winter and summer. We've reduced the operations cost compared to what it was run under the military. Yeah, it's a little bit less than half right now for annual. It went from 7 million a year to about 2. We are working to put an incoherent scatter radar at HAARP. This would greatly help us do some of the observations. It would be one of the ways to observe what happens when we change the ionosphere. And I think that one of the main messages from us is that this is a scientific community facility. The scientific community really spoke out and said that they wanted to save this facility. There was a lot of money invested in it, and it would not be recreated. It's one of those things that when these facilities are created or instruments are invested in, if you dismantle them, the likelihood that we would have it again is slim to none. So it was really important for us to step forward. Dr. McCoy has been the champion for this. He actually called some summits together in DC with the military and with the scientific community advocating for this. Senator Murkowski has helped in this, and we appreciate that. And it's open to international experimenters. So we get asked, can I visit HAARP? Well, yeah, yes you can. Not all the time. And that's mostly because, remember I said we cut down the operational costs? It's because we have a lot less staff. And so we don't have staff to support routine tours, but we do have an annual open house. And the next one is August 25th on Saturday. Jessica will be there. And it's worth the drive. It's a beautiful drive, and it's a beautiful facility, and I encourage you to attend the open house. If you have any questions, there's many ways to contact HAARP. All the contact information is here. I'm here, Jessica's here if you have any other questions about the facility. Thank you.
One quick question.
Yeah.
It seems like you could almost make it a military weapon if you could control the ionosphere, such as the GPS wouldn't work.
So so you mean you would kill the, you're not actually you're not actually destroying the GPS satellite itself, you're just changing whether or not it could work. Because it could be the other way around too. You could actually enable the satellite to work if it was disabled in some way. So it depends on how you look at it. There's also possibilities to do over-the-horizon communications. Because of the frequencies, it's possible to ping submarines. So there are some obvious military applications for it, but it's all based really in communication. So it's either GPS satellite or radio communications itself.
So if you had a strong enough HAARP, could you create an image that CLEAR might mistakenly pick up as a solid object when it really isn't?
No, not in the nature, not the way that CLEAR does their detection and the way that the ionosphere does the work. So it's in a different location, in a different way that it manifests itself. Yeah, CLEAR watches everything. They watch all of the satellites and all of the objects. Yes?
In the picture of the glow, we saw streaks. Were those satellites going by or shooting stars?
So the ones that appear and disappear, those are shooting stars. Satellites you usually see go from, like in the image, it goes from beginning to end. I mean, it depends on what orientation. It might look like it's going down, but yeah, you'll see satellites. When you can see satellites outside at night, on a clear night, and they look very unnatural, right? Because of the way that they move. Yeah.
Excuse me.
Yeah.
Is the facility working? Have you been obtaining good scientific results in the last 30 years? Because I listened to the experiment you showed, the image.
Was from
15 years ago.
Yeah, that was from the Air Force, right? Yeah. So, he wants to know if we are getting scientific results now. So let's see if I can go back in a way that doesn't drive me nuts. Maybe not. So we talked about what we've been doing since 2015. I think I said that. So this is how many campaigns we've run. We've only run 3 campaigns and one more. And yes, they are scientific campaigns that got scientific data.
The data was useful.
Yeah. Yeah, it's good science.
So I guess I can speak a little bit more to that. So the funding agencies for the...
Wait. This is Jessica Matthews.
So the funding agencies for the 3 campaigns at the university have run have been under the National Science Foundation, the Department of Energy, Los Alamos National Lab, University of Alaska, obviously, Air Force Research Lab, and Naval Research Lab. And obviously it takes time to write some of those papers, but on our public website for HAARP that Nettie's given that address for, we have a list. It's not complete, but there's been a tremendous amount of science and work that's been done. We have publications listed for HAARP research from 1990 to 2010. So that's 20 years of research that's available. You can certainly deep dive into all of that. It's available on our public website about the kind of work that's going on down there. So that's a good question. I appreciate you asking it.
Anybody else?
What's the frequency band that you're working with?
So it actually is quite wide because you can tune it. So you're going to correct me if I'm wrong. 2.7 to 10 megahertz.
2.8 to 10 megahertz.
Yeah, it's
2.7 megahertz.
yeah.
It's 2.8 to 10 megahertz.
Okay.
Yeah.
Yes, sir.
Yes. I feel like I should be handing you the mic, but okay.
I think one of the most important things to point out about HAARP, which you have, is that the power available is 12 megawatts.
Yes.
And the efficiency gets down, and so the most power that can be radiated is 3 megawatts. And just as you don't see Volkswagens at drag races because they don't have the power, 3 megawatts compared to what the sun is putting out is peanuts. But I also have to say, your question about why are there conspiracies, I happen to have bought this book at Tidal Wave Books a couple of years ago. It's The Ultimate Weapon of Conspiracy. And the next book in the series is Lost Continents and the Hollow Earth.
I'll be waiting for that to come out. Yeah. Yeah, thank you. So yeah, on the power, because of the way that it works, it's about 45% efficiency purposefully. And so you're right, compared to the sun, it is small. And I think, compared to what we have available to us, it's quite large. You figure 1 megawatt can provide the power for about 1,000 homes. So it's about, when you start thinking about that, it seems very large. But when you think about the sun and the aurora and the things that we see naturally, it's quite small. Yeah. I saw other hands. Yes.
So, to me, I think of an antenna as being not necessarily durable, but obviously a structure that large has some sort of, durability. For operating it during winter, is there any extra work that you guys have to do as opposed to operating it during summer to basically keep it functioning?
So that's a real housekeeping question. Do you want to take that? She's so glad she came tonight.
This is my son. So that's a good question. It's really just a work rest cycle for folks when you operate at that site down at 40 below or 70 degrees above zero. And so it's just making sure that we're smart about the work that people are doing when they're operating and performing maintenance in the area. So no, the equipment itself was built for Grinnell, Alaska.
Yeah, and I think that Jessica brings up a really good point about the work-rest cycle that happens, and we have the same thing here at UAF with, or at ASF with our antennas. It's the same concept. So antennas, just like babies, want your attention usually in the middle of the night and at winter, right? It's kind of a given. But the equipment itself is usually pretty robust. It's just whether or not you have the staff to do the turnaround repairs at the right amount of time. And the nice thing about it is we are Alaskans, so we're robust too.
The experiments that they do, are they mainly in the summer, winter, or just a mix?
So this facility can actually operate all year round. Not all of the ionospheric heaters can, but this one can. And so we've seen a mix. It depends very much on what they're studying and what the intent of the experiments are. But we've had two in the summer.
Right, and it depends. I'll give you an example. Like for the optical.
You have to wait till you have this.
Sorry. I'm under 2 seconds. Like for the optical experiments, you obviously would not want to do that in the middle of summer here in Alaska. So depending on the science, that's when you determine whether it's going to be a winter or a summer campaign. Optics obviously prefer night or winter activities.
Yes.
You just mentioned that compared to other ionosphere heaters, so there are others?
There are others, yeah. This is the biggest and the best, of course, here in Alaska. But it's actually true. There's some in Norway, Russia. There's actually 2 in Norway, right? And then 1 in Russia. And then Arecibo in Puerto Rico. So there are other ones around. And depending on how many antennas and how much power, et cetera, it kind of depends on what's built out. But we're not the only one. We're just the biggest. Yeah.
Your aerial photograph showed an aircraft radar site. Was that to protect the viability of the experiment or the viability of the pilot?
As a pilot, I'm going to answer the pilot. Yeah, so that's a warning device that ensures that people are not flying over when it's radiating.
Is it a highly dangerous situation to fly in that deep? That's what I'm really asking.
I don't think so. No, but it's still it's not even a restricted zone, right? It's a so if you look on your charts, normally restricted zone is like you simply do not fly into there, and it's not classified as restricted. Hey.
So under the Air Force, they operated on what's called a controlled firing area. And so it was really incumbent on the site itself. When there was an aircraft within about 5 nautical miles, the site was shut down to ensure that general aviation could transit the site. Under the university, we transitioned to a temporary flight restriction. So from the surface to 25,000 feet, the FAA helps us control that airspace. And if a general aviation aircraft needs to come through, we shut the experiment down.
So the plane is not going to hurt the experiment. Yes. Oh, sorry.
What's the difference between a campaign and research?
So the campaign is the time that you're actually running the facility and using the staff and all that for that. But the research part of it starts way before the campaign and goes way after. So it's when you get the data, you have to first design the experiment, then you have to sell the funding agency on the concept that it's worthy of doing, because it costs money to run the facility. I think the cost right now is $5,000 an hour to run HAARP, and so you have to get a funding agency to agree to that. That's all still part of the research. Then you run the campaign, you gather the data, you process it, figure it out, analyze it, and figure out if you need to do another campaign or if you need additional information and in order to write the paper. And really, it took me a long time to figure this out, but the university, the output or the product of university, we have 2 products, students and papers. So we are required to write the peer review articles on the science that we do. So that's really how we prove and continue moving our programs forward. And that's all, to me, the science and the research. But the campaign is 15 to 130 days. I am not giving you the mic again. No, I will, but after her.
So when I hear about this or whatever, it sounds like this is another gathering tool for research, like the ship that the university owns, the Sikuliak.
Yeah.
And there are probably other things that, as a non-scientist, I don't even know anything about. But for the marine research, I can think of things that might help with our environment and some of those problems. And I guess I still don't understand enough about what your product can do for us, for all.
Okay, that's fair. So yeah, it's a really good analogy. So the Sikuliak is our big ship that we have now, and it's owned by NSF and operated by UAF. And so it's a very good analogy. A large, expensive research vessel, right? We can say it's about the same thing.
And rent out time on it.
And rent out time on it, it's very, very similar in concept and in scope. So the product that we have is really talking about how can we ensure communication continues, how can we, it's both radio, so land-based, and GPS, satellite-based communications. And when you think about an emergency situation, for example, how can we ensure that we can continue communicating, either with each other or with the lower 48 or with Europe or whatever we need to do? How do we continue and not lose that communication line? So that's the primary output.
I'm sorry, to follow up on that, communication will not be interrupted in case of what? I mean, what sort of event would happen where that would, where the HAARP would come into play?
There would be a couple of things that could happen if, for example, we lost our communication satellites for some reason, or and you can actually use HAARP to communicate over the horizon. If we lost, if we were blocked, I think that you brought that up a little bit, and it is possible to use it or for someone else to block our communication abilities, change the ionosphere. That's if you're thinking that it's something nefarious. But what if it's just the sun, which is really the thing that changes things the most, is the sun. Big prominence, a big coronal mass ejection. Solar flares go in 11-year cycles. In the top cycle, we're just being hit by all sorts of irregularities in the ionosphere, and it breaks up the communication. How can we mitigate that? So that's part of what we're studying.
And was that the military's original concept with the HAARP, and was that what they were?
The military's original concept was really focused on communication, yes. And it was both land-based radio communication and satellite-based GPS.
So to piggyback along the communication lines, I mean, you mentioned submarines during the presentation, and that's traditionally very low frequency waves as opposed to very high frequency waves. So I'm wondering, I mean, do you guys still do research along those lines of communicating with submarines, or is that mostly stopped since, the Navy has departed the site?
So for the 3 campaigns that we've done so far, we haven't done one of those. So whether or not that would happen is if following that research cycle where a scientist or a group of scientists comes in, does a proposal, and pulls it forward. So we have the capacity to do that. It's not something that has happened. I mean, we're just really starting in a lot of ways. We got the facility in 2015. It's taken a couple of years to get it up and running. And we're out there canvassing for people to come, okay, the scientific community, you wanted to save this, then come help us support it.
How many frequencies can be used at the same time?
It's multiple. Yeah, it's basically, because it's tunable, you can, and it's a phased array, you can use the whole array of frequencies that are available. So it just depends on how you want to tune it. Yeah.
How much longer do you think it'll last as a useful facility? I mean, with its design life, I guess not an economic life.
Yeah, those are, economic life is unpredictable, but design life, I don't think it's anywhere near its end.
I guess, are you talking about infrastructure or what?
Yeah.
Like the antennas themselves?
Yeah.
So Nettie talked about what's called an educational partnership agreement. So that was what the university had with the Air Force, and the Air Force transferred to the university about $41 million. and equipment, and that was the research instrument that Nettie talked about. The facility itself is just under $300 million. It's in exceptional shape. The Air Force took great care of it. We have absolutely the right people on site that know how to conduct the operations and the maintenance of the site, so it's in outstanding condition.
They also, it was a type of spares. So the Air Force also, in that, they supplied the university with spares. And when I was out there with Jessica, every time we'd open up an office or a container, there would be spares. Like it's just chock-a-block full, which is exactly what you need in Alaska, right? We know that in Alaska we want all the spare parts right there, ready and available. And so the Air Force was very generous with that.
Can the frequencies go into the earth to figure out if there's some low density areas inside the planet?
I don't think we've ever gone down. We only go up. Okay.
So there's a lot of really great questions, and the principal investigators that have been doing a lot of the research have helped us with a fairly comprehensive public website. If you guys see the website there, Sue Mitchell here, the GI Public Information Officer, helps us to maintain a list of the frequently asked questions. You know, do you guys kick out chemtrails? Are you controlling mines? What kind of research do you do there? The publications, like I said, we have about 20 years of publications. It's not a complete list, but you know, we inherited this from the Air Force. So I'd love to be able to speak to all of the Air Force and the Navy's intent and DARPA's intent, and we just don't have that. We're moving forward with the program. We do the best we can to try to consolidate all the really good questions that people ask us, then to be available and ready to answer questions the best we can. So if we don't have that specific answer, I encourage you guys to go to this website or contact us. And if we don't have the answer, we'll do the best we can to find out for you.
Yeah, there's a place that you can do that. And the other thing I wanted to say about the facility is that it was designed by scientists. And we talked about this a little bit on Monday when I was out there. Because when scientists design things, they design things for as many possibilities as they can possibly afford, right? They want it to be flexible and to be available for different things, and to try and design something for the things you haven't thought of yet, right? That's the way a scientist designs something. That's why they become very expensive pieces of equipment, and very useful. An engineer and a group of engineers will tend to design something for a very specific purpose and stick to the specs and try to do better with the costs. Luckily for us, the Air Force and the Navy got together and they built an exquisite scientific instrument that we now have. And some of the experiments that it can do, we have not even tried yet. And so there's a lot to be done. There's a lot of potential here. Pretty exciting that UAF has this. And I'm happy that you all came out tonight. I really appreciate all your questions. And I'd like to thank Jessica Matthews for being generous with her time as well. And we can talk afterwards, but I think that's it for tonight.